Happy Thursday, guys. Let's see how much we can bust out today. None of you are freezing, hopefully, yet, but let me close the door. Because middle schoolers are about to be noisy in the hallway, and the air can turn off faster. Whew. What was I doing at the end of yesterday? Not that I'm going to go all Fortnite on you, but what was I doing at the end of yesterday as far as this stuff? Yeah, I could, well, I can't, literally, but some of this could go into it, but we'll forget it. What was I doing? Graphing polynomials of higher degrees and thinking about going side to side. What's going to end up? Now, guys, you see that these are nasty functions, right? That's not, none of these are as simple as these guys. Why? What's so different about ones on this page, these graphs on this page than this one? This page says monomials only. Can I have a number there? Sure, whatever, I don't care. Can I have a number, but only one term. X squared, x to the 4th, x to the 6th, x to the 16th. I could have you guys pick whatever A's you wanted, and they're all going to be, all the even degree terms are all going to look like little polynomials. Sorry, no, parabolas. Either facing down. What could you do to A to make it face down? Put a negative number, okay? So if you, right now, took out your calculator and all of you just chose some x to an even number, could be 32, could be 112, could be squared, could be 16th power, and you chose whatever A you wanted, as long as it was a real number, not imaginary, which I don't think you can plug in your calculator anyway. Positive or negative, they're all going to be parabolas, either up or down. Some of them are going to be super narrow, especially if you do like a huge number, a huge degree. Maybe it's super narrow, but it's still going to be a parabola. Why? It's only one term. There's no like plus or minus that's distorting it somewhere else. Same thing here. You could choose any n, any odd degree with any a, and either it's going to be going this way, or what happens if you put a negative number? That way. But either way, it's this way or that way. It's going to be a cubic function. It's going to look like a cubic function. Why? Because it's only one term, but all of a sudden we say, wait a minute, polynomials way back here in the very beginning, didn't we talk about? Took a lot longer than I thought. How there can be m plus 1 terms. So if I did do x to the 32nd, how many other terms could there be of a possible 32nd degree polynomial? 33. It could have the 32nd, 31st, 30th, 29th, 28th, all the way down to the first x, like x to the first power, and a constant. Hi. All sorts of stuff in between the ends. So here's the idea. When we do the leading coefficient test, oh, too far. Well, I'll show you these graphs. When we do the leading coefficient test, we're not saying what's going on in between. We're like, we have no idea what's going on in between. We're just looking at the ends, or I think, Lauren, is this what you said, to the sides? We're just thinking as you go to the sides what's happening. So check out these guys. If n, hold on, pause. Did we actually write down who n is? Oh, we didn't, did we? I think we did in the last section. Didn't we talk about how n is degree, right? Just in case you guys forgot, n is the degree of the polynomial, aka the highest power of x. Okay, n is the degree, if you need to write it down, aka the highest power of x in the polynomial, okay? So if the degree is even, the highest power of x is even, n behavior, we can say to the left, and we can say to the right. Now, I think you guys can fit this in one line. I'm going to go ahead and kind of split it up, but I think you guys can fit it in one line. So let me just fill in what's going on. To the left. I'm not saying from the left. I'm saying to the left. I want you guys to think to the left is headed west. Okay? So as you head west on this graph, question, what's it doing as you keep on going west, going west, going west? Not like the middle, but eventually. What's it doing? Rising. The function is rising. And what's going on to the right? What's the function doing? Rising. Oh, so this function's only rising. No. No, it's not only rising. I mean, actually, if you're talking about increasing, decreasing, isn't it decreasing, increasing, decreasing, increasing, decreasing, increasing? But what we're saying is just the ends. As you go to the left, as you go, if you want to think from right to left, as you go west, it's rising eventually. And as you go to the right, it's rising eventually. So how would you guys fill out this end behavior? What's going on if an even is having a leading coefficient that's negative? Good. To the left, I can say the function is falling. And to the right, the function is falling. So to the left, function is falling eventually. There's stuff going on in between maybe. To the right, the function is falling. So rising and falling, those are the words that we can say. And to the left is pushing west, and to the right is pushing east. And it's saying eventually what's going to happen. Not quite sure how adding and subtracting terms is going to have some little like bumpity bumps along the way in between, but what's going on to the right, to the left? So then as we go down here, first even, now odd. For end behavior, when we start adding all these extra terms, what's going to happen to the left? The leading coefficient of an odd degree polynomial. The leading coefficient is positive, falling. Good. I'm going to replace the word function with f of x, because I'm talking about the y values. To the left, f of x is going to be, now I'm going to introduce a term for you. Arrow. You guys are totally right. The function is falling to the left. But I'm going to introduce notation to you. F of x is approaching, ooh, hey, little arrow in math, means approaching, going towards, headed. Yes. No, it's a good question, but yes. Standard math notation with graphs, we're always reading the graph left to right. Now this one's a little weird, but that's another reason why the arrow is going left to right. But f of x is going to be approaching. Oh, how can I explain this mathematically? The word is falling. Totally right. The function is falling. But how can I explain that with like where it's headed? Negative infinity. I can say falling by saying the y's are headed towards, are approaching negative infinity. That's like a mathematical way of saying falling. So what do you think I'm going to fill in if I'm trying to show a mathematical expression for what's going on to the right? What's the function doing? Rising. So how do I say that? F of x is approaching positive infinity. So what switches if my leading coefficient is negative? To the left, what's going to happen? Isn't it a reflection, guys? So isn't it just going to, aren't these just going to flip orders? Instead of f of x approaching positive infinity to the right, now it's approaching positive infinity to the left. It's switched. And then what's going to be happening to the right instead? Okay. So on this page, I described the end behavior two different ways, and they're both correct. One way is to use words and say something like, oh, to the left, the function is rising. To the right, the function is rising. To the left, the function is falling. To the right, the function is falling. Evens, odds, depending on the leading coefficient, either both going up eventually or both going down eventually. Did I just say evens, odds? Sorry, even degree. Depending on whether the leading coefficient is positive or negative. Always agree, eventually. But then there's also a mathematical notation to saying rising and falling, and that's down here. You guys can see the falling. You can see the rising, hopefully. But the notation is the y's approach negative infinity when I'm falling, or the y's approach positive infinity when I'm rising. I just want you guys to be able to recognize that if you ever see an arrow. It means approaching, getting closer, closer, headed towards negative infinity going down, positive infinity going up. Now here's the crazy thing. I replaced the words rising and falling with this notation. But what did I not replace? Let's zoom in on that real quickly. Because technically I still used words. I didn't want to totally overwhelm you guys all at once. So let me replace the words also. To the left. A mathematical notation to the left. F of x's, y's are rising and falling. Y's are heights. X's are left, right, whereas y's are down, up. So the whole rising, falling thing, I needed y's. But for the left, right thing, I need x's. And to the left, x is going to be approaching. Yeah, where's x approaching if I'm headed left? Negative infinity. Negative numbers and more negative. To the right, which way on the number line is x going? Positive infinity. So I can actually take all the wordings from up above and I can actually put really snazzy math notations to them. To the left, x's. X's are the left-right measurement. To the left, x is going to negative infinity. To the right, x is going positive infinity. Falling, y's are approaching negative infinity. Rising, y's are approaching positive infinity. So this page has a lot. This page not only reminds you of even degreed polynomials, but also odd degree polynomials, like how they behave, but they also, this page also, shows you how the wordings can be put into snazzy math notations. Okay? I'm not going to make you write the next 2 pages. I just want you to look at them. Does it make sense then if, for an odd degree polynomial, we have no clue exactly what's going on in between, but do these notations make a little bit of sense? This means to the right, and this means, got it, to the right I'm rising. This means to the, and this means, and that makes sense. Is that okay? So what's the new symbol? The arrow. And what's the arrow mean? Approaching. Getting closer and closer and closer to. Y's is a direction up, down. Up, down. X is a direction, not up, down, but right, left. And so right would be positive, left would be negative. Just reminding you guys of how Y's deal with heights and X's deal with horizontal measurement, Y's vertical measurement. And the idea isn't really that hard. It's falling to the left, or to the left it's falling. It's rising to the right it's rising. But I want you guys to see the notation too, because the arrow is super, 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 super important in chapter 12. Guess what the last chapter is this year? Chapter 12, which is limits, but okay, moving on. Does this notation make sense? To the right, rising. To the left, falling. Oh, rising. Why? Oh, it's even. It's even. It's going up, yeah. To the left, falling. To the left, to the right, falling. Wow, I'm having issues with my words. But it does make sense with the behaviors, right? So let's keep going. I want you guys to describe the end behaviors, not knowing exactly what the graphs look like, not going to your calculator and plugging into y1, y2. I have little white boxes over the graphs. We're going to compare in just a second to see if your answers are correct or not as far as the end behavior. This could also be described in the book as using, instead of describing the end behavior, they could say use the leading coefficient test. Same thing. Looking at the term with the highest degree, looking at the leading coefficient or the coefficient of that term. So whether they say end behavior or whether they say use the leading coefficient test, I want you guys to go ahead and fill in the following. As x approaches negative infinity and as x approaches positive infinity. I want you guys to fill that in for all 3 of these. What are the y's doing? What are the y's doing for this one? What are the y's doing for this one? And what are the y's doing for that one? Ooh. Struggle. You can write down the functions. That's okay. Look at the functions. Think about the function's leading coefficients. And how would you describe what the y's are doing? And practice using that little arrow notation. Sad day. I'm just struggling. Oh well, you guys see the middle one. See if you write it right though. How could you describe what the f of x's are doing, what the y's are doing? You could use words, technically, but can you figure out how to use the notation? I'm not giving the answers quite yet, but I'm seeing if you got the idea of the notation. This is how they all should start. In the back of the book, when you go to check these answers, they're going to actually use words, the word version, like rising and falling, and that's okay. It's okay. It's technically answering the question. I'm just having you guys practice the really snazzy future notation. If you don't know how to write it, why don't you go ahead and write the words as to what you think is going on. If you have an odd degree polynomial with a negative, if you're not quite sure how to write the notation, either give me a rises or a falls, or a falls or a rises, or a rises and a rises, or a falls and a falls. Just give me the words, if nothing else. That way you can check and see if your logic is right as to how the graph on the ends is behaving. Couple more seconds. If worst comes to worst, just put little words. What do you think? Rises or falls, falls or rises? And if you need to, maybe it's not a bad idea. Hey, what would I fill in? To the left or to the right? Maybe it's a good idea to put words here too. Which is this one? To the? Yeah. You guys agree? X's, horizontals going to negative infinity, x-axis going left. Good. And this one would then be to the, yeah, to the east, to the west, to the left, to the left. You could change the song. To the x going to negative infinity. It doesn't quite ring as well. You guys might have no clue what was going on in between, but I want you to see, was your logic matching up? Was your logic matching up? And now let's see if you actually wrote the notation correctly. Was your logic matching up, first of all? And then let's see if you were matching correctly. Oh, I stole his circle. Go back. Okay. To the left. Hopefully you guys, as x approaches negative infinity, you put a positive infinity because it needed to be rising. To the right, hopefully you put a negative infinity. It needed to be falling, right? To the left, hopefully you guys put positive infinity for the left and right because they were both rising. Even degree, positive coefficient. And this one to the left, hopefully you put negative infinity. It needed to fall. And to the right, positive infinity. It needed to rise. Odds are always opposite in the end behaviors. Evens are always together. So if you were putting the words you would have had, rises, falls, rises, rises, falls, rises. Okay, there's some crazy notation that showed up, but is the idea really that complicated as far as the leading coefficient test? You ask yourself two questions. One, is the degree even or odd? And then two, the leading coefficient, is it positive or negative? And as long in your mind as you have it attached as far as even, together, up or down, odds, opposite, either down, up, or up, down, you'll be fine. Just practice this new notation a little bit, or even just use the words to the left and then rising or falling, and you're okay. But we have more to talk about. Leading coefficient test, aka end behavior. Whew, check. Number 2, zeros. Wait a minute, that's not new. We've done zeros this year. What are zeros? Okay, true. 0 is 0. What are the zeros of a graph?
When the graph
touches what? The x-axis, x-intercepts. That's where the name zeros, specifically talking about x-intercepts. Cool thing is, been doing this since the first week of school because we did it in our graphing calculators. The 0 feature only found x-intercepts alone. So here's a couple things. Still saying n is the degree. That hasn't changed. N is still the degree of a polynomial, aka the highest power of x. There's a tricky word on this page. As you guys are writing, there's a tricky word on this page. At most. It's a bummer. Yeah. At most means, well, it could have at most this many, but maybe it has fewer. Hold on, Joe, not yet. Maybe it has fewer. Polynomial has at most, but maybe it has fewer. We hate maybes in math because it's like, oh, stink, I have to figure it out. Yeah. But the nice thing is this section 2.2, the factoring, why am I talking about the factoring will not get much more complicated than you've already seen, which is the good news. In this section, factoring doesn't get much more complicated to what you've seen. And you'll see it, you'll feel it when you do homework. You're like, okay, it's not too bad. Because if you guys notice down here, I'm saying for section 2.2, go look for GCFs first. Your polynomials are going to be 4th degree, 3rd degree, 5th degree, 6th degrees, but there are going to be GCFs that make the factoring really easy to getting down to something like a quadratic where you can use the x method. It's not going to be that way for all of chapter 2. We're going to have to review synthetic division and long division. And a factor theorem to go looking for factors when it's more complicated than the x method in quadratics. But this section, there are GCFs. Find them first. Factor them out. And then factor, we can say with the x method or with the quadratic formula. Factor with the x method or with the quadratic formula. Remember the modified x, a times c. If you have to do a times c with b, don't forget to do grouping. But we practiced that the other day. Quadratic formula, maybe you want to write it down if you haven't yet this year. X equals negative plus or minus squared minus 4ac all over 2a. Okay. Joe, what's up?
For the polynomial, for its even power, it at least have one.
Backwards. You have it the wrong way.
It is
Think n behaviors. Could be none. Has to be one. Mm-hmm. So Joe's giving us an extra clue. Giving us an extra clue based on the behavior of the graphs. Is it possible for a parabola, just the most basic even degree polynomial, is it possible for a parabola to have no zeros? Yeah. If you guys were in honors, we would have done this whole worksheet with vertices, maximums, minimums, completing the square, even some word problems, etc. And they kind of got a little more practice. So they were a little bit more ready for this idea. But for you guys, let's just think about the weirdest the basic monomial could be. How could a polynomial, I should say, a parabola have no zeros whatsoever and not ever hit the x-axis? Shift up. So the vertex is up and concave up. Or the vertex is down and concave down. Are we going to have any zeros? No, because the ends go the same direction. There's no guarantee it's going to go up there or no guarantee it's going to go down there. Doesn't mean it couldn't, but no guarantee for any sort of even degree polynomial. So for n being even, could have none. But why did Joe say if it's odd? Joe, don't tell him the answer. You're the one that brought it up. Why did Joe say if n is odd, it must have at least one? What if I have all this funky stuff going on? Oh, look, it's not going to hit. Wait, odd? The n behaviors always have to be opposite. So eventually, what's it going to have to do? It's going to have to cross through the x-axis. Or if I had something crazy down here, eventually, what's it going to have to do? It's going to have to go up. So because odd, they go different directions, odds will always have to have at least 1 0. Evens could have none. Just depends. But what does this say? Depending on the degree, it could have up to whatever the degree is. So if you have a 30-second powered polynomial, you could have up to 32 zeros. Oh. Oh. In order to have 32 zeros, what's going to have to happen in between? Yeah, wiggle, 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 wiggle. That works, right? It's a little Humpty Dumpty, all whatever. Bouncy, 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 bouncy. Ooh, hey, finding Christopher Robin. Bouncy, 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 fun, 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 fun. Anyway, so, yeah, if it can have up to n real zeros, there's going to be a lot of wiggle, wiggle in between. Okay, let's move on. This section is not saying that you're going to be able to, by the end of it, graph any and every polynomial, no matter how nasty. That's not what this section is about. It's about, will you have the general idea of what's going on? So we've talked about the end behavior. That's good. We're going to deal with this function for the rest of class, this guy. So write him down. He's going to be the example we're going to use over and over and over and over and over again. Maybe you even want to get a different color out, because we're going to keep on coming back to this function for the rest of class about all the other clues that we're going to deal with in section 2.2. But we're starting here just with the zeros and the maximum turning points. And then we're going to talk about a few other things, and then we're going to come back to this function and apply it. Then we're going to talk about a few other things, and then come back to this function and apply it. And by the end of class, we should have a pretty good idea of who this guy is without ever having gone to our graphing calculator. First thing, zeros. Whoosh. Page before, I said factor. Wait, that's not the first thing. I apologize. First thing is set y equal to 0. First thing is set y equal to 0. Second thing, factor. And I told you this whole section, look for the, Joe started saying it, GCF. Who gets to come out? Would you guys have pulled out as much as you could? The negative 2 comes out and an x squared? Okay, who's left? Why is it x squared minus 1? Real quick, some of you, your brains are just like, take it out, I got it, I'm done. Some of your brains are like, remember when you factor out, what you're doing by pulling out is you're taking away multiplication. Taking away multiplication is the same thing as division. Taking away multiplication is the exact same thing as division. So just in case you forget what factoring does, when you factor out, you divide. And so the negative 2 is reduced to be a positive 1. X to the 4th over x squared reduces to be x squared. 2 over negative 2 reduces to be negative 1. X squared over x squared reduces to be 1. Done. Am I done factoring? Now some of you might be able to say, oh, hey, I know the zeros. That's easy. X equals 0 and then plus or minus 1. You're right. But what would the factors be to get that answer? Technically, you would have needed to keep going to get x plus 1, x minus 1, differences of squares. I'm not going to review all the factoring today. A squared minus b squared factors to be a plus b, a minus b. Remember how we solved for zeros? We set each one equal to 0. So we'd have negative 2x squared equals 0. We'd have x plus 1 equals 0. X minus 1 equals 0. And with some pretty quick math, hopefully we get the 3 zeros. 3 zeros, wait a minute. On the page before, we said any nth degree polynomial could have up to n zeros. Where's the 4th zero? Actually, it is there, but we'll talk about it in a second. You're like, no, there's only 3 numbers. Just wait. The maximum number of zeros was 4, and the maximum number of turning points, we can have up to 3, because it's n minus 1. So the maximum number of turning points, we're going to have up to 3 turning points, and the zeros we could have up to 4. But where that 4th one is has to do with this little bottom note called repeated zeros. Maybe there are 4 zeros, but 1 was repeated, and so we just don't see it. Repeated zeros. When factors are raised to a power of k, we say that the factors or the zeros have a multiplicity. Have a multiplicity of k. Guys, make sure this isn't just like an example in your head. Make sure you make a note of this. Maybe put a star by it. Maybe get a quick little highlighter. We're going to talk more about multiplicity in just a second. But if we have repeated zeros, does anybody see the repeat on this page? This guy's a 2 for 1. Why is he a 2 for 1? How many x's were there in this 0? There were actually 2. X times x. A fourth degree polynomial needs at some point to have an x and an x and an x and an x. 4 different x's being multiplied together. I see 1, I see 2, I see 3, 4. And both of these x's both had zeros of 0. I could actually rewrite this. Give me 1 second, Joe. I could actually rewrite this to be negative 2, x minus 0 squared, x plus 1, x minus 1. And I'm not wrong. There were 2 different x minus zeros. There were 2 different linear factors with a 0 of 0. Only one factor with negative 1 and only one factor with positive 1. So just to get us ready for what's about to come, this 0 would have a multiplicity of 2. These zeros would each have a multiplicity only of 1, which is weird, right? Multiplicity of 1. Isn't multiple more than 1? These ones have a multiplicity of 1 because of the power their factors are raised to, whereas this one would have a multiplicity of 2 because of the power of x it was raised to. Joe?
Just because we don't have positive 0 or negative 0, such a thing, so it just happens to be 0.
Yeah. I think he's thinking like quadratic formula plus or minus square root, but since it's just a 0, the plus or minus, there's 2 that get the same answer. Yeah, that's one way of looking at it. Probably a little bit harder for a lot of people to visualize, but yeah. So we have 4 zeros, technically, 0, comma, 0, comma, negative 1, comma, positive 1. But on the graph, how many intercepts are there going to be? Only 3. Pause for 1 second. I'm going to get you guys to start writing this, but I'm changing this year. I'm changing how I do sign charts. So let me have you guys write that down. But as I have you write that down, let me go get my new way of doing sign charts. I forgot I hadn't put it in yet. Trying to make it a little bit easier for you guys. But the book says something really weird for this. It doesn't say make a sign chart. I mean, I think it's in there somewhere. But in the directions in the homework, it's not going to say it. Oh, I already have it open. I forgot. Where are you? Sign chart, sign chart, sign chart. Nope. Yes. For those of you guys that started homework, you probably didn't get this far, even if you did start homework. I'm thinking you would have gotten this far. But towards the end of homework, you are going to have these problems that, well, basically just give you tons and tons and tons of directions, like an A and a B and a C and a D. I'm going to go ahead and give you the new formatting for sign charts. I'm also going to write the wording as the book is going to say it for this step. And just a warning, for those of you that follow Calc Chat maybe a little too closely, my way is different than their way. My way is the way I want you to go on this. They're going to say something to the effect of plot sufficient solution points. The most ambiguous direction that you're going to see in a math problem in pre-calculus all year. They're going to say, plot sufficient solution points. You're like, plot as many as I need? I don't need any. Look, I can graph it on my calculator. Done. No. No, no, no. When they say plot sufficient solution points, I want you guys to think sign charts. Sign charts. You will have just found the zeros for the function. In these types of problems, you will have already found the zeros or the x-intercepts in a step before. So you'll already have the zeros, and you're going to make intervals out of those zeros. You're already going to have the zeros. You're going to make intervals out of the zeros. Actually, for you guys, I'm going to make this chart even a little bit easier than I did for pre-cal. Sorry, for honors pre-cal. Because I'm going to add, if it lets me, I don't know how to do tables as well in, will it let me? Maybe it won't. Okay. Nope, I don't want that. I'm going to change this up just a little bit. That's awkward. Why? Oh well, I give up. Sorry, it's awkward spacing, but we'll deal with it. Remember how I said we're going to use that one example for the rest of class? We're going to use this sign chart for that example that I just had on the board. So let's go ahead and take the example that I just had. Let's do this. There we go. Let me show you how this works, okay? For this example, we just found our zeros. I want you guys to think about a number line, like an x-axis, that's been split using these zeros. We're not even going to the y yet. We have 0, we have -1, we have +1. We have 0, we have -1, we have +1. Can you guys see, even with these zeros, like if I was just to say, like, hey, mark zeros on the x-axis, this number line has been sectioned into 4 parts. Do you guys see it? 1 and 2 and 3 and 4. Can you give me interval notation for each of those 4, starting at the left and working your way right? What would be the interval for the far left one? Interval, x interval. How left to how right? How left does this little piece go? -infinity. How right does this little piece go? -1. Keep it open, just like we did for increasing, decreasing. Now it should be easy. Jordan, it's pretty warm in here. Go ahead and take your hood off. Thanks, kiddo. -infinity, -1. What's the next interval? -1 to. Good. Keep going. Next interval.
0 to 1.
Good. Next interval.
1 to infinity.
Perfect. All we did is wrote down intervals for the number line. That's it. How hard is that? Not bad, right? What's the next column say? Test x values. A test x value. Right down here it says check the sign of f of x in each interval using test points. Test point. Look, a test point in the interval. Oh, well, who's an x in between -infinity and -1? Choose whatever you want, but choose wisely, because whatever you choose, you're going to have to. There's -137. Huh. Choose what?
-1.5.
Ugh. I don't want to plug in a fraction, Joe. How about -2? Could you have chosen -1.5? Sure. Do you want to? Probably not. -2 sounds good. Oh, which means wouldn't 2 be a nice easy one for that interval?
Yeah.
Sweet. Do we have many options for these guys? Well, yeah, we have infinitely many. -1.7654. No. Let's just do -1/2 and 1/2. Is that okay? I mean, we're stuck doing a fraction anyway. Oh, well. So what is this guy saying? Take them and plug them in. Remember, we're doing this for this example, so some of you might be using your other color to say, like, oh, hey, P.S., we're using it for the example. So now we're going to go plug in -2. So what is f of -2? What is f of -1/2? What is f of 1/2? Is this going to take a little bit of time? A little bit. But can I give you guys a hint? Do you think it'll be easier to plug into this form, raising something to a 4th power, soon 1/2 to a 4th power? Or do you think it'd be easier to plug into this form, where you have like little broken up math facts? Do you want this one where it's all with powers, or this one where it's broken up? I think broken up's easier. because the math facts are a lot faster. That's just my advice. You do whatever you want to do. By hand, practicing your mental math. Okay, my ones who would just go to their calculators. But I would go ahead and do -2 times -2 squared, -2 plus 1, -2 minus 1. Now some of you are like, I could do that mental math. Yeah, me too. So that could be -2 times 4, -2 minus 1 is -3. I could change that just to be that. And then can't I multiply left to right? -8, +8, -24. Haha. You know what's really snazzy? This is an even function with even symmetry. You plug in a -x, nothing changes. I can actually kind of cheat and say this one's going to be a -24 also. Or you could plug it in and figure out it's -24. But this guy has symmetry, which means what's going on at the -x also goes on at the +x. That's cool. How about the -1/2? Oh, okay. -2 times -1/2 squared times -1/2 plus 1 times -1/2 minus 1. Some of you are like, I can mental math that. I'm like, so we could do -2 times 1/4, 1/2 times 1/2. -1/2 plus 1. Does anybody know an easy mental math way of doing that? You add 2 over 2, and you get +1/2. You subtract 2 over 2. You get -3/2. And pretty quickly, I think you end up with 3/8. And this one's 3/8 also. Guys, guess what you can do if you have the zeros, if you know the end behaviors, and if you do a sign chart to plot sufficient solution points? You can actually say, let's take all this information and let's say, I know there's a 0 there, there's a 0 there, there's a 0 there. I know this guy is way down low, this guy a little bit up, this guy's a little bit up and way down low. I know end behavior, he's going down forever and he's going down forever because I have a negative leading coefficient. I know he has to go through this 0. He's going to bounce off that one. He has to have smooth turns all along the way. And I'm pretty sure this is pretty close to what he's about to be. The one thing that we didn't get to write down was how I knew, wait, pause, how I knew it was crossing through and then bouncing has something to do with the multiplicity. If the multiplicity is 1, it always crosses through. If the multiplicity is even, it also or always bounces off. Cross through, bounce, cross through, and that's a really good picture of the graph that I am supposed to be finding. Get out of here, work the best you can on homework. If you come to something called the intermediate value theorem at the very end of homework, you don't have to have it attempted for your picture tomorrow. Bye, guys. Intermediate value theorem at the end, just leave it. Just leave it. She was making up her test. Yeah.